and welcome to this session on OpenTelemetry and more specifically, the OpenTelemetry collector. So to give a brief outline, we'll start by giving an overview of the OpenTelemetry project and its functionality. We will talk about the collector and its architecture, and from there we will go to the main section of this presentation, how to configure the collector. We'll have some live demos that show how to configure and deploy the collector, and the goal is to help you be able to configure the collector for whatever your use case is. But before we get too far, let's get started with some introductions. A little bit more about me. My name's Curtis Robert. I am a software engineer at Cisco. I've been working in the observability space for about 2 years now, and I'm currently an approver in the contrib distribution of the OpenTelemetry collector. Next up, my co-presenter, Steve.
Thanks, Curtis. My name is Steve Flanders, and I'm an engineering leader at Cisco. I've been involved with the Open Census and OpenTelemetry projects since the very beginning and have more than a decade of experience in the monitoring and observability space, including leading log initiatives at VMware, distributed tracing with Omnition, which is now the Splunk APM product, and now metrics as part of Splunk infrastructure monitoring. I'm currently writing a book about OpenTelemetry, and I'm excited for it to launch later on this year. All right, so let's talk a little bit about what OpenTelemetry is first before jumping into our topic. So OpenTelemetry is an observability framework and it's a toolkit, but at the end of the day, it really provides 3 building blocks. It provides a specification, which is basically an open standard on which everything else is built, and this is what really allows and empowers OpenTelemetry to be an open standard. On top of it, you have instrumentation libraries, which is a way across different languages to instrument an application, generating traces, metrics, logs, and additional signals, as they're called in OpenTelemetry. And then there's a data collection component known as the OpenTelemetry collector, though there are other collector components as well. The collector allows you to ingest, process, and export telemetry data. And we'll be talking more about that soon. Now, why does OpenTelemetry matter? At the end of the day, there are several kind of factors at play here. One is it is a single open standard that anyone can adopt, whether it is an end user, another open source project, or even vendors. And it's vendor agnostic, which means it's not going to lock you into one particular observability platform at the end of the day. It gives you flexibility and choice. Second, OpenTelemetry really empowers you to have data portability and control. If you want to send your data to multiple different observability backends, or if you want to change where the observability data is going, you have the flexibility of doing that with OpenTelemetry. In addition, you control your data. So if you want to, for example, provide like CRUD metadata operations, you can do that with the OpenTelemetry components that are available. Now, OpenTelemetry is the second most active project in the CNCF behind only Kubernetes, which I think really speaks to the fact that this is a problem that needs to be solved, and it's adopted by a wide range of end users that also contribute to the project, and it's supported by every major vendor today. In addition, there are a variety of open source projects that also have OpenTelemetry integration, including Kubernetes, Istio, Prometheus, and Jaeger. Now, let me tell you a little bit more about the OpenTelemetry collector, which is kind of the primary focus of this talk. The collector, as kind of mentioned, is a single binary that can be used to ingest, process, and export telemetry data. It actually supports all signal data, so you can deploy a single agent or gateway instance in order to collect traces, metrics, and logs. And it's very flexible through its pipeline configuration, which we'll be demonstrating here shortly. Now, if you think about a reference architecture, the 2 most common ways in which the collector would be deployed is as an agent that can actually be with the application itself, as a sidecar, or if you're in like Kubernetes, as a daemon set, so you can do like one per host, even if there are multiple applications on that host. That's very common because it really offloads responsibilities from the application itself, the instrumentation, allowing the agent to kind of perform operations like buffer and retry logic. Or it could be deployed as its own standalone instance, typically referred to as a gateway. This is usually clustered, so there's usually multiple of these instances, and this can act as kind of a data aggregation or filtering layer. For example, if you wanted to do tail-based sampling, you would do it with the gateway instance. Or if you wanted to collect from, say, the Kubernetes API, where you only want to do that once, again, you could do that with a single gateway instance. So it's possible to have your OTel instrumentation send to a locally running collector agent. It could have that collector agent sending to a gateway cluster, and you can have that gateway cluster sending to one or more backends. Now, of course, the collector is entirely optional. You don't have to deploy it in either of these ways. In fact, you can have instrumentation send directly to your observability backend if you want. Again, the whole point here that OpenTelemetry is providing is flexibility and choice every step of the way. All right, now the collector is a Go binary, or it's written in Go, and it has different packaging that's available. So you can, for example, deploy this very easily on Linux, Windows, or Mac OS. In addition to this, it works very well in containerized environments, and Docker containers are provided. And there's even packaging specific for Kubernetes for the more cloud-native workloads as well. Now, if you want to create your own, again, you could do that, right? The building blocks are in place. So if you need other packaging options, they are available. Perhaps more important, though, is that the collector has this notion of distributions. A distribution is a specific set of components that are bundled with the collector itself. If you think of the OpenTelemetry repositories, which are hosted on GitHub, the collector has two main repositories. The first one is core. It is located at OpenTelemetry-collector, and that has all the core components that are required for a pure OpenTelemetry environment. For example, OTLP, which is the format in which all data is transformed into in OpenTelemetry, has a receiver and an exporter available in the core distribution. Now, the contrib repository, which is available at OpenTelemetry-collector-contrib, this actually has a wide range of receivers and processors and exporters. For example, this is where commercial vendors or even open source vendors would have their receiver or exporter components available. In addition, it contains functionality that you may or may not need. For example, if you want to do CRUD metadata operations, that would be a processor, and it exists in the contrib repository. So it's very likely that you need some amount of components from core and contrib at the end of the day. Another packaging model that's available is, in terms of distribution at least, is Kubernetes. And in the case of Kubernetes, it's actually packaged in Helm. So there's a Helm chart available. There's even a Helm operator. And that packaging ensures that you have the components required to collect data from everything that Kubernetes has to provide. So there are actually specific receivers and processors that are enabled for you there. Now, the great part here is that there's actually a utility available that allows you to create custom distributions of the collector if you need it. So if you want to pick and choose which one of these components you're pulling in, you can do that. That is great for mature production environments where you're looking to really reduce the surface area of things that could be configured, and it gives you a lot more control of the collector instance itself. Now, let's jump right into the configuration because that's the primary part of what we want to talk about today. I want to show it first, and then I'll be turning it over to Curtis to give us a nice demo of how this all ends up playing out. So to do that, I have to talk about the components a little bit more in depth. So receivers are how you get data into the collector. These can be push or pull based. That means, for example, if you're familiar with tracing, trace data is often pushed from the application to a collector. That would be a push-based receiver. Now, in the case of metrics, if you're familiar with Prometheus, it's very common that some endpoint is actually being scraped. The application metrics are being scraped themselves. That would be an example of pull-based data collection. Both those are supported. There's a wide range of receivers. Processors are what you do with the data after you've collected it. So if we go back to like tail-based sampling or CRUD metadata operations, those would both be processors. And you have a lot of control there on how you want the data to be processed. Then you have exporters, how you get data out of the collector. Again, this can be push or pull based depending on the configuration. And then extensions. Extensions are usually things that don't touch the data themselves. Two very good examples. One would be like health check information for the collector instance itself that's available as an extension. Or let's say you want to do something like authentication or service discovery for your receivers or even your exporters. Those things are usually available as extensions as well. The newest component available is this notion of a connector. A connector is unique in that it's both a receiver and an exporter. It actually allows you to reprocess information, either the same or different, after it's gone through a pipeline in the collector itself. A little bit more of an advanced use case. You typically wouldn't be starting with a connector component, but it is available for use as well to ensure that you have everything that you need to fully process data in your environment. Now, the collector is configured through YAML, very, very common in cloud-native environments, for example, in Kubernetes, and it's really a two-step process. So all of those components I talked about, they have to be defined and configured in this YAML. So on the top half of the example that you see on the screen, you will see things like receivers, processors, and exporters being defined. And you can define more than one of them. So for example, if we look at receivers for a second, you'll see that there's a host receiver that's being configured, and that allows you to collect metrics, and you can see that it has a custom configuration where certain scrapers are being defined. And then you have an OTLP receiver that's defined. And because there's no additional configuration there, what that actually means is it's taking the default configuration that's available for the OTLP receiver today. Now, just defining these and configuring them doesn't actually enable it. So the next step here is actually to define what's called a service pipeline in the collector. And service pipelines are signal specific. So you'll see examples here of both metrics and traces. And that's where you actually define like which receivers, processors, and exporters, or even connectors, are at play here. So if we look at the metrics example for a second, it's going to take that host receiver, it's going to do some batch processing, and then it's going to export it via Prometheus. You can see a similar example for traces. Now, what's really interesting here is that there's flexibility in that you can receive in one format. So let's say we're looking at traces here, we're receiving an OTLP format, but we're actually exporting in Zipkin format. That's what allows the collector to actually be vendor agnostic. It can receive data in one format and export it in a different format. And in addition, you can have multiple processors. So if you want to perform multiple different pieces of processing before this data is exported, that's totally possible as well. The order of processors actually matters. So it's actually done in the order in which it's defined in the list. And that's important because maybe you want to sample before you filter or do CRUD metadata operations, or maybe you want to actually do CRUD metadata operations before you sample. So depending on your business requirements there's a lot of flexibility and choice every step of the way. And worth noting, it's actually the host metrics receiver, so that's just a typo here. These receivers are all defined within the GitHub repositories. So let's go ahead and look at those GitHub repositories. Where am I going to find out what all these configuration options are and how I can define them? We're going to go to the GitHub repo. That's why I talked to you a little bit about those distributions. Here we are in the contrib repository, and we're actually looking in the receiver folder, and you'll see that there are actually multiple receivers defined. So if you're not using the contrib distribution, if you're using core, you would have to use a different repository here. You drop the hyphen contrib at the end. And then if you didn't want to do receivers, you want to do processors or exporters or connectors, you would change to that particular folder, and you would see everything that's available for that component set. Now, let's go ahead and open up one of those. So here I am going back to the core repository. So we're in OpenTelemetry collector. We're underneath receivers. We're looking at the OTLP receiver, and you'll see it has some great getting started information. It gives you an example of that configuration file at the end of the day. It shows you what options are defined and configurable, as well as what their default options are. And there's even advanced configuration options with links to that as well. So again, kind of rich getting started information. All of it's available in the GitHub repo. It's actually not in the OpenTelemetry documentation site on opentelemetry.io today. That will likely change in the future. Now, there's a few other ways you can actually configure the collector as well. For example, you can use command line arguments. So if you want to define this as you're starting the OpenTelemetry collector binary, you can do that. You can do more advanced things, like within this YAML configuration, you can actually define environmental variables that'll get expanded for you automatically, providing a lot more of a dynamic configuration if you need it. And then there's a newer part of the OpenTelemetry project called the OpenTelemetry Transformation Language, or OTTL. It's actually a DSL, or domain-specific language, that OpenTelemetry is creating and adopting, which will make it much easier and a much more standard way to define configuration going forward across the project. That is experimental or in development mode today, but it's actively being developed and getting richer and richer by the day. Okay, so instead of me kind of showing you through two slides, I think it's way more powerful to actually see a demo of this live. So I'm going to turn it back over to Curtis, and he's going to show you exactly how you can configure and use the collector.
All right. Thank you, Steve. So now that we have a basic and general understanding of the telemetry collector, how it works and its components, let's jump into a demo. So for the sake of simplicity, I'm going to be focusing on just running the collector directly on my local system. So as Steve mentioned earlier, we come to the releases distribution of our collector, and we find the binary for our own system. I'm running on Mac and AMD processor architecture. So I just downloaded this file to my local system and I can run it from there. So I'll pull up the command line and I will get started with a basic configuration. So to run the collector locally, you simply specify a config file, --config, and point it to your config. So in our demo, we'll start with a very basic configuration and we'll just build from there. So as Steve mentioned earlier, the collector is made up of different components. We have the primary types are receivers, processors, and exporters. So in our basic ground up demo, we'll just start with a receiver and an exporter. And Steve mentioned this already, but the host metrics receiver is a good place to start. It just scrapes your local system for data and sends it through your metrics pipeline. So in the README here, we have information about how to configure the host metrics receiver. One thing to know is the collection interval, how frequently you want to scrape your local system for data. And then also take note of the scrapers. So since I'm on Mac, some of them are not compatible. CPU, disk don't work on Mac. So for our demo, we'll just use memory. So we'll come back to our configuration file and we'll specify receivers, host metrics, collection interval, I will say 10 seconds. And then for scrapers, as I said, we'll just use memory for now. As far as exporters go, I'm going to use the debug exporter. It's always a good place to start just to make sure that data is coming through as expected. So we'll define a debug exporter. And verbosity is good to just say detailed to start out so that you're getting the output that you can. The debug exporter just sends all the data that's coming through your pipeline to your standard error logger. So we have a receiver, we have an exporter. The next step, we have to define a metrics pipeline that the metrics will actually flow through. So it goes under service, pipelines, and then metrics. You can have multiple metrics pipelines. You can have logs, traces. For this demo, we'll just be doing metrics. So we want a receiver here, host metrics, as we define exporters, debug. Okay, you can define as many components as you want, receivers, processors, exporters, connectors, but if they're not a pipeline, they will not be used. So make sure to include any component that you want to use in the relevant pipeline. So now that we have a basic collector configuration set up, we can come over to our command line and we can run the collector. Okay, it started up successfully. I'll just stop the collector there. We can see the output, and we come over here and we see that we're getting our memory metric successfully. So the system.memory.usage shows the bytes of memory that are in use, and then we have different data points down here. So we have a data point for how many bytes are being used, we have a data point for how many bytes are free, and we have a data point for how many bytes of memory are inactive. So next, the demo, we can add a processor. And for my demo, the resource detection processor is a good place to start. This will be able to add resource attributes to the metrics flowing through your pipeline. And in my case, I want to use the system detector, which will add the host name of my computer and my OS type. So we'll come back over to the configuration file. We will specify a resource detection processor, and we will use the system detector. So what this allows us to do is to filter metrics based on where they're coming from. So in whatever backend you're using, you can see all the metrics from a specific device or environment, and you can see if something's going wrong or if something's abnormal. So we want to make sure that we add our resource detection processor to the pipeline. We'll save it. We will run the collector again. Oh, I messed up. Invalid key detector. Okay, it needs to be plural. All right, so now we see our metrics are still coming through, but now the resource detection processor has detected my local OS and it's detected my machine's hostname. So now any metrics coming through the processor and its pipeline will have the system information attached to these metrics. From here, I think the next step is to send our data to somewhere more useful. So I will use Prometheus for this. So we can look at the Prometheus exporter. It allows us to expose metrics at a specific endpoint that can then be scraped by our Prometheus environment. So I will define a Prometheus exporter. We have to set an endpoint, and I will use localhost 8889. This is the default port for Prometheus, and I have set up my Prometheus environment to scrape this endpoint. And then the other configuration option that is helpful here is resource to telemetry conversion. This says to add resource attributes as labels to Prometheus metrics. This will make sure that we still have our host information attached to Prometheus metrics. So resource to telemetry conversion enabled true. And then we have to add Prometheus to our pipeline. And we can run the collector again, and we'll check to see if Prometheus is getting our metrics properly. All right, it started up properly here. And we'll go over to Prometheus to output. And I'll start here to see all of the metrics that Prometheus is scraping. and we'll see if the metric that we're looking for came through. So we see here system memory usage bytes. So we can notice that this metric is named differently than what we saw in the debug exporter. This is simply because of Prometheus's naming conventions being different than OpenTelemetry. So the metric name gets converted to Prometheus format. So we can come over to the Prometheus search and we can look up system memory usage bytes, and we can see our data that is being scraped by Prometheus. A couple things to note, we can see that the host name is coming through properly. So in Prometheus, we could filter base name, and also that the state is coming through properly. So Prometheus shows that we have memory coming through in different states, and we can view the graph and see how that changes over time. So our free bytes are pretty low. We have inactive bytes, and then we have used bytes. So from here, we can add another processor, and we can filter out data points that we may not be interested in. So this will help us reduce our resource usage, and that way we don't have to ingest metrics that we don't care about. So for this demo, I think I will use the filter processor to filter out points that are not interesting. And in this case, I'm just going to filter out inactive memory bytes. So the filter processor has the configuration options, and we're just going to find an example that looks close to what we're looking for. So we have some ones that are close here. We just want to filter out data points based on metric name and attributes. So we'll define a new processor, filter, error mode ignore, since this is just a demo. And we're going to be filtering metrics, and we're going to be filtering by data point. So here we're going to define the metric name, and note that this will be in the otel naming scheme, not Prometheus. The metrics are converted to format in the exporter, so when they're coming through the processor, they're still in the otel naming scheme. So the metric name, system.memory.usage, and then the state that we're trying to filter out is inactive. So we'll filter by state, inactive. So what this does is any data point that is in the system.memory.usage metric and has state inactive will be dropped by the filter processor. So we will restart the collector since we're changing the configuration. Oh, messed up the configuration again. Oh, inactive needs to be a string. All right. Okay, the collector has started successfully again. So let's go over to Prometheus to see if we're properly dropping inactive data points. So we will search again. All right. So we see here that there's a short break in metrics where the collector was down. We see that before, when the collector was running, we had used, we had inactive, and we had free memory bytes. But now that the collector has restarted and we're filtering out the inactive data points, we're not seeing those data points anymore. So the filter processor is working as expected. So now in our configuration, we've successfully added a receiver, multiple processors, and an exporter. We're sending our data to Prometheus. We're filtering out data points maybe not useful for us, at least in this demo. And we are able to view our metrics in Prometheus. we wanted to share a more involved example of the power and capabilities of the collector. So we'll be using the official OpenTelemetry demo. This will allow us to deploy the collector in a Kubernetes environment and to configure it and observe a website built from a microservices-based architecture. And that's what the demo is. So let's view the architecture. So the demo is a website that is a store. So you can browse different products that are for sale. You can add them to your cart. You can check out, add your personal information like your address, credit card, and you can order. So as we see here, we have different microservices running that handle different parts of the website. And as the legend shows, these microservices are written in quite a few different languages. We have .NET, C++, Go, Java, JavaScript, Python, and many others. So for each of these microservices, we have the languages, SDKs, instrument the microservices, either manually or automatically. So these microservices are instrumented to send their telemetry to the collector. So if we scroll down a little bit, we can see that the data is flowing from the demo to the collector. And there's a link here to the collector configuration. It's a bit hard to follow the flow of data in the collector if we're just looking at the YAML file. So for the sake of the demo, we can use otel bin to visualize the flow of data. So in our pipelines, we can see that we have traces, metrics, and logs. In our first demo, we only had metrics. So this will be helpful in showing us how other telemetry works as well. For traces, we see that they are coming through the OTLP receiver, which is defined here in the configuration file. We're able to receive traces over gRPC or HTTP. And then these traces, when they're coming from these different microservices, will go through the batch processor and then be sent on to these exporters. We have the OTLP exporter, the debug, and the span metrics connector. So the connector introduces a special use case, and we can look at the span metrics connector README to see what it does. But first, general overview of connectors. Connectors can be used to connect different pipelines of telemetry. So here we see that the span metrics connector is an exporter in the traces pipeline, but then it's listed as a receiver in the metrics pipeline. So the span metrics connector is able to generate metrics from your traces, and those metrics will go through the metrics pipeline. For more information, we can read the span metrics connector README. So what it's doing is it's generating metrics based on the spans that flow through the collector. It's able to generate request count metrics and metrics for error counts and the duration of spans. So this allows you to search your data in different ways. You can view your traces, and then you can view the same data, just formatted differently and compiled in metric format. So coming back here to the configuration, we have the metrics pipeline. We have the HTTP check receiver. We have the Redis receiver and the OTLP receiver as well. And all of these receivers are going through the batch processor, which then sends data to the OTLP HTTP exporter and the debug exporter. For logs, we have the OTLP receiver, the batch processor, and the OpenSearch and debug exporters. A couple things to note here. You're able to use the same component declaration in multiple pipelines. It's not a problem. Another thing, the order of receivers and exporters in your pipeline does not matter, but the order of your processors does matter. Your data is flowing through one processor after the next in order, so the order is very important. All right, coming back to our architecture, from the exporters alone, it's hard to know where the data will end up going as far as your backend is concerned. So the architecture shows us what else the demo is spinning up. And the demo is spinning up a Prometheus instance, Grafana, and Jaeger as the backends. So on the left, we have metrics, and metrics will be going to Prometheus and Grafana. And our traces will be going to Jaeger and Grafana. I've deployed in Kubernetes. There's another help page to show how to do this. By default, there's a load generator running in your environment to mimic what a real load would be for your website. But for the case of this demo, I have turned it off so that we can see our own usage information. So let's go to the website and take a look around. Okay, go shopping. All right, so here we have the different products available that we can buy. The comment book looks nice. Pick up a few of those. And let's see what other items are recommended. Okay, the optical tube assembly looks expensive, so let's do that. And we'll pick up a few. All right, now that our items are in the cart and we're ready to check out, we'll just confirm our information. Make sure it all looks good. And we can place our order. So here we see our order is complete and everything looks good. So let's go see the telemetry that the microservices have generated from our instrumentation. So we can go to Jaeger. One view that is helpful, I'm sure other backends have this as well, but it's helpful to see the flow of requests through our architecture. So the traces coming into Jaeger are able to generate this view that show us where a request goes when we're interacting with the website. So when we go to checkout, especially, we can see all the different services that the checkout service depends on. If we go to search, we can view traces for specific services. So I'm going to take a look at the front end service and find traces that have gone through the front end service. We're looking for the post operation because this will show us the different durations for checking out and buying items from our store. So we can see some services take quite a long time, and some services are very fast. And this view helps us see another large value proposition of OpenTelemetry and the collector as well, in that these microservices are written in very different technologies, different languages, and so on. But with our instrumentation and sending traces through the collector, they can all be viewed in the same format and in the same chart to look the same. This helps a lot with being able to reduce our mean time to resolution for outages and to be able to search information in a uniform way. So from here, we can go take a look at our Grafana instance, and we see a few dashboards that are there for us automatically. So we can take a look at the demo dashboard, and we can see, usually we can see different data coming in from the span metrics, and there's another dashboard for that, so we'll take a look there. But we can see logs coming from the add service. We can see that most are just informational severity, but we are getting a couple warnings. So if we're running into any issues, we can see logs that may point us in the right direction. We can see the number of each log message and the number of logs at each severity level. We also have information around the microservices and how they're working performance-wise. All right, we're back. We'll take a look at other dashboards. We can go to the collector dashboard. Here we can see the rate of data coming through the collector itself. So we can see how many spans are coming through, how many metrics and logs are coming through. We can see the general performance of the collector. We can see how much memory it's using, and so on. And as mentioned earlier, we can come to the span metrics demo dashboard, and this will show us the metrics that the span metrics connector is generating. So latency here shows how much latency there is, how long the spans take for each service. On the top right, we have how many requests per second each service is getting. You can see some are used much more than others. And then we have error rates, so we can see if any microservice is hitting a lot of errors. So that was a short overview of the OpenTelemetry demo. We saw how to deploy in a Kubernetes environment with the collector. We saw the collector's configuration for receiving telemetry of traces, metrics, and logs. And we were able to see how useful all this data can be in different backends. We saw how we can detect outages quicker with traces and metrics, and we saw different ways to find the root cause of issues. We hope this gives more insight into the full potential and capabilities of OpenTelemetry and the collector as well. And we hope this was helpful in learning how to configure and use the collector. Thank you.
That was a very cool demo. So as you can see, it's really easy to get started with the OpenTelemetry collector, and it's extremely flexible and able to handle pretty much any use case that you can think of today when it comes to data collection. There's a wide range of components out there. We didn't have time to cover all of them, but the basic process you follow across the board. Go find the GitHub repository that it's being hosted in, go find the component itself, and there's rich README information and examples there, even test data that you can use in order to kind of try out these components. And the components cover a wide range of environments or use cases today, so it's very, very feature rich, and new ones are being added all the time. So if you're not seeing something that you need, go ahead and file a GitHub issue, or feel free to come contribute to the project. We always welcome people to contribute here and kind of expand upon what is available. The goal is to provide as wide of coverage as possible. Now, the collector is very, very powerful, right? A single binary that can be deployed in a variety of different form factors that allows you to ingest, process, and export your telemetry data. And it really gives you this vendor agnostic solution. Very easily can transform data from one format into another. And that's because under the covers, it's using OTLP, right? The collector converts everything to OTLP, and that allows it to do it in a standard way to perform different processing capabilities before that data is emitted from from the collector instance. Now, again, you don't have to use the collector. It's just available there to provide some capabilities that you may be looking to generically solve for. It can eliminate some of the proprietary aspects of using a vendor solution here, and it can even help you consolidate the number of agents or collectors that you're deploying because it can actually support multiple different signals for you. Now, if you're looking to learn more, there's plenty of documentation out there. We kind of showed you some on GitHub, but there's also the OpenTelemetry IO site, which has some rich getting started information, how to like bootstrap the collector as an instance in different environments, as well as taking a look at the demo environment that Curtis was referring to. So definitely encourage you to kind of take a look at some of the material out there. And again, feel free to contribute and add more. The more documentation we can provide, the easier it will be for people to kind of get started. So thank you so much. We hope you enjoyed this talk. We hope you learned a few things about how the collector can be used in your environment. And if you have any questions, feel free to ping us on the CNCF Slack instance. Curtis and I are both very active. Thank you so much, and we'll be chatting soon.